Volume Calculations 1. Integration of cross-sectional area. Consider a solid whose cross-sectional area is given by a function a of some variable x. That is, assume that we can define a coordinate axis along which the area of cross-sections perpendicular to that axis is a function of position along the axis. Then, we can imagine approximating the solid with layers whose volumes are given simply by cross-sectional area times thickness delta x. Summing such layer volumes will provide an approximation to the volume of the solid, and as delta x gets smaller, the approximation should improve, and in the limit, as delta x approaches 0, we should obtain the exact volume. These approximations are Riemann sums that converge to the integral of the cross-sectional area over an appropriate interval on the coordinate axis. All this essentially just means that volume is the integral of cross-sectional area. Example: a solid's base is the unit disk in the xy plane, and its vertical cross-sections parallel to the y-axis are squares. Find the volume of the solid. To get a picture of the solid here, imagine first the xy plane lying horizontally as shown here with the unit circle, which is the base of the solid. Here's a typical vertical cross-section parallel to the y-axis, or perpendicular to the x-axis. And this is what the solid looks like. Now, approximations of the solid look like thin square blocks. Summing the volumes of such blocks gives an approximation of the volume, and as the thickness delta x approaches 0, these approximations approach the integral of the cross-sectional area. Since the base of the solid extends from -1 to 1 on the x-axis, the limits of integration will be -1 to 1. So our job now is to find a formula for the cross-sectional area A of x. So let's look at the unit circle in the plane. Each cross-section is a square whose bottom edge extends from the bottom half to the top half of the circle. At the top, y is equal to the square root of 1 minus x squared, and at the bottom, y is minus the square root of 1 minus x squared. So the edge length of the square cross-section is 2 times the square root of 1 minus x squared, which means that the cross-sectional area is the square of 2 times the square root of 1 minus x squared, or 4 times 1 minus x squared. This will be the integrand in the volume integral. We'll use symmetry here to rewrite the integral from -1 to 1 as 2 times the integral from 0 to 1. So, anti-differentiating, we have 8 times x minus 1/3 x cubed evaluated from 0 to 1, which equals 8 times 1 minus 1/3 minus 0, or 8 times 2/3, which is 16/3. This is the exact volume of the solid. Example: a solid whose base is the planar region in which y is between 0 and 2 times 1 minus x squared has square vertical cross-sections parallel to the y-axis. Find the volume of the solid. This is the base of the solid. Note that it extends from -1 to 1 along the x-axis. Now let's make the plane horizontal and show a typical cross-section. And here's what the solid looks like. We can approximate the volume by summing layer volumes given by A of xi times delta x, and as delta x approaches 0, these approximations converge to the integral of A of x. The limits of integration are x equals -1 to x equals 1. Now let's look again at the base of the solid. Each cross-section's bottom edge extends from the x-axis up to the parabola, and so its length is simply y equals 2 times 1 minus x squared. Therefore, A of x equals y squared, or 4 times 1 minus x squared squared. So the volume of our solid is the integral from -1 to 1 of 4 times 1 minus x squared quantity squared dx. We'll use symmetry here to rewrite the integral from minus 1 to 1 as 2 times the integral from 0 to 1. Now we multiply out the integrand, anti-differentiate, and evaluate between 0 and 1. So we have 8 times 1 minus 2/3 plus 1/5 minus 0, which after a bit of arithmetic ends up being 64/15. Example. The solid's base is the planar region in which y is between 0 and the square root of 1 minus x squared, and its vertical cross-sections parallel to the y-axis are semicircles. Find the volume of the solid. The graph of y equals the square root of 1 minus x squared is the top half of the unit circle, so here's the base of our solid. And here's the outline of a typical cross-section. In fact, the solid looks like this. The volume will be the integral of cross-sectional area from x equals minus 1 to x equals 1. We now need the cross-sectional area A of x. Since cross-sections are semicircles, their areas will be given by pi times 1/2 the square of the radius r. Note that the radius r is half the length of the cross-section's bottom edge. That edge length is just the y-coordinate of the top half of the unit circle, which is the square root of 1 minus x squared. So A of x is equal to 1/2 pi times the square of 1/2 the square root of 1 minus x squared, or pi over 8 times 1 minus x squared. So the volume of the solid is pi over 8 times the integral from minus 1 to 1 of 1 minus x squared dx. Again, we'll use symmetry to rewrite the integral from minus 1 to 1 as 2 times the integral from 0 to 1. Next, we anti-differentiate and evaluate between 0 and 1, and this gives us pi over 4 times 1 minus 1/3 minus 0, or pi over 4 times 2/3, which is pi over 6. The volume differential. We've seen that certain volume calculations can be done by integrating cross-sectional area. The cross-sectional area A of x times dx is a differential, which we'll call the volume differential dV. And it is useful to think of dV as the volume of a typical very thin slice with thickness dx. Now let's look at one last example. Derive the formula for the volume of a right circular cone with height capital H and radius capital R. Note that cross-sections perpendicular to the central vertical axis are circular. Let y denote the distance from the vertex. The volume will be the integral of the volume differential dV from y equals 0 to y equals capital H. Now, cross-sectional area will be given by pi times radius squared, and so dV equals pi times little r squared dy. We need to express little r in terms of y, so let's look at the central vertical cross-section of the cone. The principle of similar triangles tells us that little r divided by y here is equal to capital R divided by capital H. Multiplying by y, we have little r equals capital R over capital H times y. Now we put that into our formula for dV, and we have pi times big R over big H times y, quantity squared, times dy. This is the same as pi times big R squared over big H squared times y squared dy. And now the volume is going to be pi times big R squared over big H squared times the integral from 0 to h of y squared dy. The antiderivative for y squared, of course, is 1/3 y cubed. When we evaluate that from 0 to h, we just get a 1/3 h cubed. And now we simplify and we arrive at what is hopefully a familiar formula, 1/3 pi r squared h. It's exactly 1/3 the volume of a right circular cylinder with the same dimensions.